Welcome students to GEOS 380 Geological Hazards. This is Professor Jessica Larson with the University of Alaska Fairbanks and the Department of Geology and Geophysics. This brief lecture accompanies the hazard topic landslides and avalanches, and it focuses on the processes that cause landslides to happen. As you can see from this picture, landslides can create a lot of damage and destruction and loss of life around the world globally each year. Landslides are of concern in areas that have steep hill slopes, mountain slopes, any slope that can create sliding, mass sliding of earth, rocks, debris, downslope, carrying with it things like roads and houses, as shown in this picture. First, we're going to look at the properties of granular materials, and in this case the example given is dry sand and wet sand. If you look here, the dry sand forms a conical pile. The grains have a grain-to-grain frictional contact, and where the two grains touch in the sand pile, the friction holds them together, and they can maintain a conical shape with the slope angle at the angle of repose. If you add just a little bit of water to the sand, you get a much steeper slope, shown here with this little bucket sand castle formed by wet sand. You can see that it has a very, very steep slope angle. In this case, the slope angle is much greater because of the surface tension of a very thin film of water which holds the grains together, creating a much stickier, cohesive force that can create a much greater angle of repose. If you add a lot of water, I think you can all guess what is going to happen. It's shown here in this picture. Extremely water-saturated soil and sediment basically has no cohesive force anymore because water is completely surrounding all of the grains and it eliminates any grain-to-grain contact. So if you pour a bucket full of completely water-saturated sand out, the water and the sand together will just run out and form no slope angle to speak of because the water is carrying the grains along with it. I think it's pretty intuitive to make the connection then with this picture where we have a big mud flow that came down and ruined some houses and buried a road and knocked down some forest. You can see the water streaming out of the sediments, and you can know that this mud flow was created by very, very wet soil, water-saturated soil, where the soil lost any of its cohesive properties and was able to flow and slide downslope very easily. If we look again at the grain scale level, you can see another cartoon here where you have sand grains with films of water wetting around the grain surface and partially filling the pore spaces in between the grains here, these little pockets. When you add water into pore spaces, shown in this cartoon here, this little pore space here in between these grains, the water will actually exert pressure on the grains, forcing them apart, and this helps to also remove some of the frictional grain-to-grain contact and cohesive properties of the soil itself, and it makes the soil weaker. Whether or not a mass on a slope will slide really comes down to the forces of gravity and friction, balanced with the slope angle. If you look at the force diagram on this block here, it's resting on a slope with an angle alpha 1. The weight of the block, L, is pulled by the force of gravity, so we have a force here, L, that's pulling straight down on the block due to gravity pulling on the mass of the block. The force of gravity can be broken up into a perpendicular component, N. This is the force of gravity that pulls on the block perpendicular to the slope. And there's another force of gravity that we can break out here, which is F. This is the force of gravity that's parallel to the slope. whereas again L is the force of gravity that's pulling the block due to its mass down towards the center of the Earth. The little f here, that force, that is the force of friction. That's actually frictional contact between this mass and the slope. And the force of friction, in this case, for a moderate slope angle of 30 degrees, holds the block in place. That means that the force of gravity parallel to the slope, this red F here and the small arrow, is not big enough to create a sliding force pushing the block downslope. So the block is stuck in place on this modest slope. But if we raise the slope angle here to 60 degrees, you could see that it's a much steeper slope. In this case, you have the same force of gravity L here acting to pull the block towards the center of the Earth, given the block's mass, which hasn't changed. You have the same force N here that's perpendicular to the slope. That's also a gravitational force. Friction hasn't changed, but yet the slope angle means that this force here, F, the red force parallel to the slope, is much larger now, and the block can slide down slope. So with all of this balance of forces on the block, if you can raise the slope angle enough, this force parallel to the slope that causes sliding can overcome the frictional force sticking the block to the slope, and the block will slide. So when you combine the forces of gravity wanting to pull masses of rock and soil down slope with a steep slope angle, and water saturating the grains in the soil, the result are landslides like shown in this picture here, where we had a landslide that formed in a steep slope. This is a picture from Central America. Landslide mass of soil and rock was unstable. Gravitational forces pulled the mass down slope, and the soil was likely wet, meaning that it didn't have much cohesion or internal friction holding the grains together. Thanks for your attention in this mini lecture about the fundamental causes of landslides due to soil properties and forces acting on masses of rock and soil on steep slopes. Be sure to check the website for any additional content that you need to learn for this hazard topic. Thank you very much.